Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today, as with most of my screencasts, we'll be discussing the reciprocal system, in particular, the reciprocal system Microcosmos database. We're now in this panel on the left side here, liquid, vapor, gas, matter properties. Last week we covered volume and density. Today we're going to cover specific heat. So here we go. Click on that. There's a lot of data here. I'm taking water as the example. This part here, liquid, is this section here. This part here is the vapor properties, and then the gas properties, real gas properties are here. Now let's go through each field and I'll explain each one as we go along. By the way, there's nothing comparable to this in quantum mechanics. I keep getting interrupted here for some reason. Alright, hopefully that won't happen again. Alright. First field, of course, is the element or the compound of the mix, in this case H2O. Description, ice, water, steam, of course. Form number one. If you wanted to put in alternative properties, you could duplicate the record and then up the form number and then change whatever you want to change. Atomic molecular weight is here, melting temperature here, vapor gas symbols the same in this case. Atomic molecular weight is here. So in some cases, the vapor gas symbol will be different. Okay, the delta V, it's helpful to use the tooltips. I guess I don't even have it for this, but in this case it's 0. It's usually 0. Melting temperature in Kelvin is here, and that's calculated as opposed to the observed. And you have the option of using vapor pressure as the external pressure. I'm going to say no in this case. Alright, let's go through the liquid properties. Now, just as with the previous screen, volume and density, we have this whole list of parameters. You need to figure this out for each element or compound. This is the number of different elements of the molecule. So in this case 2, just H and O. And the number of atoms is 3. This is the number of close packed groups per molecule in the solid state. That's what the S1 is. Close packed groups per molecule in the liquid state, that's S2. And then this N initial is the number of initial units extrapolated back to 0K for specific heat of the liquid. And internal, this is the number of structural groups having internal motion. Solid-like vibration per molecule. Okay. And LTG, this is the number of liquid thermal groups per molecule. This is 1.5. The number of liquid structural groups per molecule, it's the same, 1.5 in this case. It's the number of liquid volumetric units, number of liquid temperature units, the number of units, and NP is the number of units, atoms or molecules, resisting external pressure. So this is 9. So it's like 9 grouped together to oppose external pressure. And then here we have the average CP, the specific heat per pressure, per structural group, and that's in cal per mole per K. Note this is an overall average for the different levels of structural groups in the molecule. So it's 300. These are the choices here, by the way. So there are just a limited number of choices. Of course, R is the gas constant. So it's 3R in this case. Okay, so this takes a little bit of an effort to figure these out, but these are small numbers. Everything is quantized now. In some cases, we have fractions. It's very rare. We'll have half integers sometimes, but it's a little rare, but this is because of hydrogen bonding here. Anyway, critical temperature K, calculated, observed. It's calculated 654, observed at 647. Critical pressure in atmospheres, again, it's calculated versus observed. External pressure. Now, this is an input. This is an important input. For the example calculations here, we're going to use 500 atmospheres, which is pretty high. And we're going to use 600 K for the temperature. To compare with theoretical calculations, we're going to use Carl Yaw's values from his excellent work, Chemical Properties Handbook, where he gives all the empirical regression equations for the properties of matter. That's because quantum mechanics is completely useless. But engineers need to have something, so the best that we could do before was to use empirical regression equations. So here we have the A, B, C, D regression coefficients. Alright, so now we get to calculate the specific heat. Again, this is at the temperature K, 600, and pressure 500 atmospheres. So cal per mole per K, joule per mole per K, cal per gram per K. Okay? Everything's here. Cost here we have specific heat per volume. Everything's based on mean volume expansivity. Okay? And here we have the Yaw's calculations. I mean, they're not quite as close as we would like, but that's what you're going to get. These higher pressures, I'd be willing to bet that the reciprocal system is more accurate. Okay, so now we have a situation where we have a heat sink and a heat source, and we can press this button to set TK to the mean of the sink and the source. Doesn't matter. And again, we calculate specific heat here, constant pressure. That's what the P is, of course. Cal per mole per K, joule per mole per K, cal per gram per K. And here we have the CV value, specific heat, and this is obviously the usual values here. And this is for the heat source, of course. Okay, so heat sink, all these values here, and heat source here. And then we have down here the C sub V values. I'm sorry, these are our C sub P values for the heat source, C sub P values for the heat sink, and then we have the C sub V values down here. Again, reciprocal system calculation versus the Yaw's calculation. And then here's the approximate calculation for the boiling temperature. Let's see if I have a tooltip. Yeah, the boiling point is temperature which the vapor pressure equals 1 atmosphere. Okay. Alright, so that does it for the liquid specific heat properties. Now we go on to the vapor properties. The Yaw's regression equation coefficients are here. Temperature K. Now you can change the temperature here if you want. That's for C sub V. And then I calculate C sub P, specific heat in the space above the liquid, and the specific heat on the surface of the liquid. And this part here is the cal per mole per K. Again, you have this. You have all these choices, but it's 4R and 3R in this case. Okay. Above the space, that's really the vapor. It's 4R, whereas it's 3R. And then I calculate the joule per mole per K, cal per gram per K, and then the corresponding C sub V values here. Again, you won't find anything like this in quantum mechanics. Now, the real gas, we have these parameters, and you've got to pay attention here. This does take an effort to get these values, but this is theoretical physics. So IT is the initial level in terms of natural temperature unit for 3D and 3D gas temperature. For 2D and 3D gas temperature, normally this will be 2/9, if not enter decimal fractions. This parameter is the number of thermal groups in the gas at the 2D gas initial point. Okay, NGTG1 is the number of thermal groups of gas just before going to 0 3D gas initial point or beyond. TL0K, this is the temperature of the liquid at the very beginning of the transition to gas. T sub G 2D 0K, this is the temperature of 2D gas at the initial point. TG 2.5D, this is the temperature intermediate between 2D and 3D gases. This is the temperature of 3D gas at initial point K when internal motion reaches the 3D state. So there's quite a bit of a transition between 2D motion and 3D motion here. And the calculating method for specific heat, TG2D0 to TG3D0, that's the general way. But you have a choice here if you want. Okay, so let's say the real gas is at 1000 K. And of course we have the Yaw's regression coefficients again. It's important that you get Carl Yaw's book, Chemical Properties Handbook, so you have a way to compare the theoretical calculations that I'm giving here with the empirical regression equation. So here are his coefficients A, B, C, D, and E. And then the initial values, you have a whole series of choices here, so you're going to choose that. And then finally we get the specific heat, cal per mole K, joule per mole K, cal per gram K. And you can see it's very close here, Yaw's and the reciprocal system calculation in this case. And then we have C sub V, specific heat, and C sub V, Yaw's specific heat. Again, very close. And then we have our usual heat sink and heat source calculation, where we calculate the C sub P specific heat from the reciprocal system, from Yaw's, and then C sub V. Again, it's the same, like this column is cal per gram K. And you can imagine, it's the same thing going across. It's going to be cal per mole K, and then joule per mole K, cal per gram K. And in this particular case, the calculations are very, very close for the real gas calculations, which is nice to know. Now here we have an ideal gas, the ideal gas equations. So you can see them here. And obviously they're not too bad, but they're somewhat different from the real gas calculations. And here again we have the CV ideal gas calculations for this. Okay. And then the calculation of the dissociation temperature, that's when the H2O molecule breaks up, 272963. Of course, you can add whatever notes you want. Let's see what it's... I'm going to read this. Note that the real gas volume at the critical temperature and pressure is 2/3 of the ideal gas volume at those same... at those same conditions. It's a 2D gas. Also note that in the reciprocal system, liquid specific heat is constant, whereas it is not for the Yaw's regression equation. The estimated saturation volume using an empirical equation is taken at 647.12 K rather than at 647.13 K due to numerical values. Okay, well, interestingly, the simple vapor volume calculated by the reciprocal system for water at the critical temperature and pressure is equal to the saturated volume. But this is not the case with other vapors, hence pure theoretical calculus cannot be given presently. The Yaw's regression equation does not go to infinity as it should at the freezing point. The reciprocal system viscosity values are considerably higher. We'll get to viscosity in a later presentation. All right. So again, this is very complete. Once you figured out these values up here, and I've worked them out for a number of liquids and gases, then all you have to do is enter in the temperature K and the pressure that you want to use. Let's see, where's pressure? Here, external pressure. And then all the rest of this, all the specific calculations will be calculated for you. And of course, once you put in the yaw specific heat regression coefficients, which are here, you get the yaws calculations. Okay, and I've already put all these in for water, so this should be very accurate, extremely accurate, for all the specific heats, both for pressure and for volume, for liquid, vapor, and real gas states of water. All right, well, that was pretty much in depth there. That's it for today. Please study the reciprocal system and prove it for yourself. I'm going to close out. The simplest possible treatment of the reciprocal system theory is my work, The Mysterious Universe, published many decades ago. It has all the concepts, and still in print, but it's been out there a long time. It's gotten very nice reviews on Amazon. It covers all the concepts of the theory, very little in the way of math, but it does have all the diagrams. It's the easiest way to understand the theory, but if you do want all the mathematics, please obtain my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF, 711 slides in the PowerPoint file, thousands and thousands of equations, numerous diagrams, tables, figures, everything. It'll take you months to go through it. And then once you're through with that, then you can get these two database modules, the Microcosmos database and the Macrocosmos database. Microcosmos database has or covers solid matter properties, liquid vapor gas matter properties, cosmic elements and subatomic particles, and photon properties. So in solid matter properties, and I've already covered each of these in a previous screencast, so it covers interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes, and spectra. The liquid vapor gas matter properties covers volume and density, specific heat, that's what we covered today, energy and entropy, viscosity and surface tension, and electrical and thermal conductivity, cosmic elements down here, and material and cosmic subatomic particles, and of course photon properties. It includes a great graphics program. I've already covered the Macrocosmos database in previous screencasts. Just to review, I covered the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies, nebulae, gas and dust, and voids. If you want to jump right to various videos and pictures, I just click on events there. This also includes some great graphics. Now, my theoretical physics mentor, Julie B. Larson, was also an excellent theoretical economist, and I've made his work in theoretical economics also fully computational. That's my work called Optimal Economist and Implementation of Larsonian Econophysics. It covers the microeconomics of individuals, businesses and business sectors, and macroeconomics of entire regions and countries. Completely supersedes Keynesian economics. It's extremely useful to have, especially in times of a recession or depression like we're in at the moment. Okay, well, again, that wraps it up for today. Please, please, please study the reciprocal system and prove it for yourself. Thanks for your attention.